Hello students, welcome to ME301 Vibrations and Control. Vibrations and control. Okay. So as I told today during the live session, that vibrations and controls are separate courses, but here we are joining together with a purpose though. So vibration, theory of vibration serves as one example that we will see when we are doing the controls theory. So we can take mass spring damper system there in the control theory, and that way you will be able to relate to the equations there. So, and the equations will be similar. What we get here, you will see that the same first order or second order system we are going to study there. So this will be also provide a continuity. So that way it's really good. Okay, so as I also said that theory of vibration will have a different textbook, and control theory will have different textbook. So I'm now talking about the vibrations. So whenever I say here textbook, that really means that relates to the Thomson textbook that I have already given or posted in the Google Classroom. Okay, so we will be following this textbook, and however we will be focused on only from chapter 1 to 7. Okay, now after that we will go to the control theory part. Okay, so first 18 hours, 1 hour means here 50 minutes actually, so 18 lectures what I meant. So first 18 lectures will be devoted to vibrations, and after that we will switch to control. Now for vibrations, the chapter 1 we are going to cover a little bit the whole of chapter 1, and then we will start with chapter 2. So chapter 1 basically no need to actually go through here, because all this has very basic things that you have already learned earlier, like Fourier series for example, or complex algebra, those things. So already you know. However, I ask you to go through the problems of that chapter 1, and solve it, and I'm sure you will be able to solve it, because this is what you must have studied in various mathematics courses you had, and even in high school. Yeah, so things will be something like some example is given. For example, the oscillation, the simple harmonic motion as a like vibration, the oscillation, right? So as you know, any sign, for if you write like x equal to a sine omega t, so that really means this is simple harmonic motion. It represents y. As you know that x dot will be a omega and cos omega t. Okay, so cos omega t. Okay, and then x double dot acceleration. So this is velocity, this is acceleration, and acceleration is given by a omega square, and sine omega t. Of course, it will be minus here. Right? So this you have already studied, the simple harmonic motion. So this is one example of the oscillatory motion. Yeah. So what you see from here is this A. So this is difference. Let's call this one is capital A here. This amplitude of x here A, and this is acceleration. So this is velocity, this is position, velocity, acceleration, and the whole thing here is amplitude of acceleration, a omega is amplitude of velocity, and a is the amplitude of x. Okay, so these things already you know basically. Yeah, so this is one of the examples given there. Or you can also write x as a complex number, so you can also write x equal to a e I omega t, right? So this also represent a simple harmonic motion. Yeah, so what we will see is x dot is equal to a I omega e omega t, and x double dot equal to minus a omega square e I omega t. Right, so this also, but this is also simple harmonic motion. However, this is a complex representation of the same thing. Yeah, so this is what are given in chapter 1. Yeah, so even if you don't go in details, you will be able to solve those problems. Okay, and those problems are general problems that you have already solved in your high school and during various courses you did at IIT Ropar. Okay, so those I'm not going to repeat. Yeah, so we will start something which will be new to you. In fact, whatever we're going to start, there will be something you know already, but still we have to start and then take it further. Okay, then it will be something which will be new to you. Okay, so for regarding chapter 1, this is what we will study here. Now I'm going to start chapter 2. So let's start chapter 2. Okay, so again see Thompson book, Thompson chapter 2 we are going to start. Yeah, okay, so your course actually starts from this chapter. So okay, so we will start with a very simple example. Okay, and the simple example, the physical example that you must have already studied. Yeah, so we will start something you know already. So this is a spring with a spring constant k or a stiffness k, and this is a mass m which is hanging from there. So a spring is massless here. Okay, okay, now what we are going to do is we are going to first derive the equations. Okay, so when you derive the equation, you automatically also know what are the limitations and what assumptions we are making. So as I said already, we are assuming a spring does not have any mass. Okay, so in that case, what happens? Okay, so again, you must have already studied in your engineering mechanics class ME301, or even in high school you must have this one already. So let us say you have, in this case we are not assuming anything right now. Okay, so even if this system, even if you have any space, for example, there is no gravity, but still if you disturb this mass, you will see the oscillatory motion. Okay, so you can assume here, assuming here there is no gravity here. Okay, although it will not make any difference, it will still be vibratory. Yeah? So if you have this one hanging here, and if you give a small disturbance, it will start vibrating. Right? So regardless of whether gravity is there or not, it is going to actually vibrate. Okay, but there will be a difference. The mean position will be different when there is a gravity, when there is not. Okay, so we are just assuming in this case there is no gravity also. Yeah, so G equal to 0. Okay, so and mass of a spring is also equal to 0. So G equal to 0 means gravity. Okay, it will not make any difference though, as I said, but still we will discuss about it later, okay? But right now, assume this is in a space, okay? And then what we are going to do? We are going to give little oscillation here, okay? Then we want to see what happens, okay? Okay. It will start oscillating. Or even if it doesn't, let us say the displacement of this in this direction is, we call it x. Even if we don't know whether it will oscillate or not, let us derive it first and find out, okay? We will solve the equation. Well, it should be a differential equation. Then we have to solve it. If we get some oscillatory position x as a some function which is periodic, okay? So periodic function, okay? So simple harmonic motion is also periodic function basically, right? So periodic function means, right? Periodic function as I said, okay? So this is also given in chapter 1, okay? So periodic function, when you say, that really means f x plus t equal to fx. So here t is a time period, as you know, right? Time period. So this is what I mean here is time t. So like this is not x but t, okay? Small t, okay? So this is what if any function any time varying function, if f as a function of t is equal to ft plus capital T, then you know that ft is periodic, right? So this is f is a periodic function, we call it. Okay? So f is a periodic function, you say. Okay. So we will solve for x, and if we find x is a periodic function, then we will know that x is oscillatory, right? So but before that we need to find out what equation does it follow, okay? So how to find out? Okay, so what we will do here is assume there is a displacement x from the mean position, or from the where it was in equilibrium, from there, okay? We just moved a bit, and after that we don't care how it is, what the motion is, but let us say we are talking about a position x from the mean position. Let us earlier it was somewhere here, and from here it has moved to here. So from here it has moved here, okay? And this position is x, displacement. Yeah. So we just call it x equal to displacement. So we are talking about at this position which all the forces acting on that. So of course, since the spring is attached to this mass, so a spring will be attached, hence a spring will be extended by x, okay? So equation you will have, since this is down from the mean position, so hence there will be tensile force in this spring. So this will be a stretch. When it is a stretch, that really means, since this is elastic, it will try to pull up, okay? So this will be upward force, and what will be the value of force? Value of force will be k times x, where k is the stiffness or a spring constant of the spring. So this is the force kx due to spring, okay? Okay. Now, is there any other force which is acting here? There is no other force acting on this, just this one, right? Okay. So total force, how do you write? So this is upward, and our sign convention is x downward. So this is x positive. So positive is downward. So in a way, force is negative, since the force is in upward direction. So actually F equal to minus kx, right? So total force Now what are we going to apply? Apply the Newton's law of motion, right? So apply Newton's law of motion. Okay, and what does it say? It says total force equal to m time acceleration, right? That's what it says, right? Okay, so total force in this case is, we call it total force equal to m time acceleration. Acceleration in this case is x dot. X dot is the acceleration of the mass. Which direction? Downward direction, because this is what our convention here is, what we have taken it as positive. Right? So we have x equal to ma equal to mx double dot, and hence total force is what? Is nothing minus kx. We have minus kx equal to mx double dot, or hence what equation you get? You get mx double dot plus kx equal to 0. So this is what the equation is. Now we have to solve this equation, and we have to solve this equation, and we have to find out whether this is oscillatory. Yeah, okay. But you can also relate here, however, with the simple harmonic motion, right? And how? Here x double dot is equal to minus k over mx. What you see is acceleration is proportional to minus of the displacement, and hence it is a simple harmonic motion. And from here also you know that actually omega n square is given by this k over m, and hence you know that omega n is equal to root k over m, and you know that this is 2 pi over t, where t is a time period, or you can say this is a frequency. So 2 pi f is a, if here f is frequency, so you can also say f equal to 1 over 2 pi, and you have k over m. You can also write like that. Okay, so just to relate with high school physics, you can relate from here also. Okay, but since you are in like a college, and you have already studied differential equation, so we can actually apply those things that you have learned in your differential equations classes, and we can solve this one, and we can find out what the x look like. Here what you find out is just the frequency, natural frequency, what you call it, not more than that, right? So if somebody asks you from here, given this mx double dot plus kx equal to 0, what is x, then we have to solve it. Yeah. So this is what we will do next. So let's have this equation here. So mx double dot plus kx equal to 0, which is a homogeneous differential equation of order 2. We can write also this as d square x over dt square plus kx equal to 0. Now you must have solved this equation, this kind of differential equation in your differential equations class. The difference would be in your class, maybe instead of x you had y, and instead of t you had x, but solution will be the same though, right? So in order to solve this one, since you have already done the differential equation class, I assume that you know what is the solution of this equation is, and the solutions are x equal to, will be of the form of a sine omega n t plus b cos omega nt. Okay. So this will be what the form of the equations, the solution of the equation, and actually this sine omega nt and cos omega nt both will be solution to that, and where so m d square x dt square, so not m, we write this plus k over m x equal to 0, or d square x dt square plus omega n square x equal to 0, where omega n equal to root k over m. So if this is the differential equation, solutions are solution for this one will be sine omega nt and also cos omega nt. Both will be the solution to that. Okay, you can put them and you can check. So let us say x equal to sine omega nt. You put it here, you get omega n square, then sine omega nt, right? Plus here omega n square plus, here it will be minus actually, so you get minus omega n square sine omega nt, here it will be plus omega n square plus sine omega nt, you get equal to 0. Similarly, if you put it, you get the same equal to 0. So basically what we get here is the sine omega n and cos omega n t both are the solution to that. Yeah. Now the general solution you can propose is like this one. So this is the general solution. General solution will be like that. Okay. So x equal to, we assume x equal to sine omega nt plus b cos omega nt is the general solution. Now we have to see what is the boundary conditions. Okay, so next, in order to solve, we have to find out the boundary conditions. Boundary condition. Okay. So depending on the boundary condition, the solution will be different. So originally we had a spring mass system like this one, and we are assuming it is already oscillating, meaning that goes like this one. So we can assume that when this is at the mean position, then correspond to t equal to 0. So we can assume at t equal to 0, x equal to 0. Okay. So if you put it here, what we get? We get x0 is equal to a plus b, a times 0 plus b equal to b is equal to 0. And hence what you get, solution is simply x equal to a sine omega nt. So this is your question you get. So simply you can write x equal to x naught sine omega nt is the solution of this spring mass system where omega n is equal to root k over m. So this is the solution, and what you see here is this motion will be continuous. So as long as the time basically depends on time, but this mass will keep on oscillating. That's what the meaning is. It will never stop, theoretically. Okay. So this is what the solution you get. Okay. Okay. So once we know the natural frequency, this is in terms of radian per second, but if you want to express this as a per second, so in that case you know 2 pi fn equal to root k over m, and fn, which is a natural frequency, is equal to 1 over 2 pi k over m, so which is a natural frequency. Okay. Now earlier when we started, I said assume g equal to 0. There is no gravity. Okay, because the oscillation will happen regardless of whether gravity is there or not. However, there will be little bit just a little bit complicated, meaning not really complicated, but you have to take care. You have to, in fact, think differently. So let us say if this is the configuration when there is no gravity, so g equal to 0. Now let us say you switch on the gravity. So let us say the gravity is there. So what? So there will be force which will pull it. And let us say the equilibrium is now here, like this one. Okay. So what do you get from here to here? And this value, let us call it delta. So this delta will be equal to what? So total force, which is total force in this case is m times g. G is in this case g not equal to 0. So total force is mg, and what happens? This is equilibrium, is not oscillating right now. So mg will be equal to k times delta. So you have k times delta equal to mg. Okay. So what you get, you can find out k from here basically, right? So you get k. So k equal to, you get m, or rather you can find out k over m. So k over m will be equal to g over delta, right? So k over m equal to g over delta. So you can write down actually fn equal to 1 over 2 pi root g over delta. So you can express like this one. However, it should not be confused. Because of the gravity, this will come down. Yeah, it will. However, now this becomes the equilibrium position. In this case, this will oscillate about this equilibrium position. In this case, it will oscillate about this equilibrium position. This is the only difference. Okay, it will not make any other difference. Okay, so when you have like this one, you have additional expression to find out a mutual frequency, because k over m in this case will be equal to g over delta, where delta is the difference between when there is no gravity and when there is gravity. So the difference between the mean position in both the cases, and that delta you can use g over delta, and that you can put that in this equation and you get fn equal to this. So that is the only difference. Okay. Now we will see some examples. Basically, the example here we just wrote, drew a spring damper system, a spring mass system, so K and M. However, there could be, this could be in different form or shape. So, for example, like you studied in solid mechanics, you had a beam. Okay, we assumed beam to be massless, so it is massless, but this is a cantilever beam, so one end is being fixed, the other is free, and you are putting a mass here, M. Right? So this is also equivalent to that. Why? Because this beam if you apply, let us say, a force P, then what happens? This will deflect. So this will go like this, and let us say the difference between the two is, in this case, it will be x, right? So if you not x, but in this case it will be, let's say, call it delta. So this is let's call it delta. So what is the relation between that? So this is a static again, right? This is a, the present course is a dynamics course, right? So but what we did earlier in solid mechanics was all static. So this relation though, if you apply a load here, then there will be delta will be given as, you can actually solve it, okay? So PL cube over 3EI, right? So this is how the expression you get. So this is same as saying that P over delta, in this case you can actually find out. So this is a displacement and this is P. So K is equal to P over delta, and that will be equal to 3EI over L cube, right? Okay, so this is K, so this is equivalent to a K only, so this is equivalent to a spring basically, right? It is something like a spring, and then on top of that you are putting a mass. This is equal to K, this K equal to P over delta is equal to 3EI over L cube, and on top of that you have a mass M. So you see, this and this are same basically, equations will be same. Only thing is, in this case you had omega n over, you had K over M. In this also you will have omega n over root K over M, and where K is nothing but 3EI over M L cube. So this is what omega n will be in case of a cantilever beam, right? Similarly, there will be many other examples, right? So this is just one representation. This is the lumped mass system, the general stiffness we are taking, but this we can apply to any other kind of system. Here, when it is going to oscillate, here also there is a cantilever beam. If you apply here, and you must have seen, if this one end is fixed, the other end is free, you had a load here, and then little bit of disturbance, it will keep on oscillating like this, right? So this is what it will happen in this case. See another example, and the other example will be the rotational spring example. So let us say a shaft which is hanging from ceiling, and this is a rotor. This is a shaft. So shaft will have some polar second moment of area. So this is polar second moment of area, okay, and which is given by, so half times certain area, then R square. So this half and pi d over 2 square, then d over 2 square. So this is half pi d over 2, 4. So this is IP. Yeah. So this is polar second moment of area. Then this is a rotor. This is a rotor, and we are assuming this is massless. But the rotor has some mass, or has J. In this case, we will differentiate between J and IP. IP we studied in solid mechanics as IP equal to J, but here this is now J is mass. This is second polar second moment of area, and this one is a mass moment of inertia. So we write it as mass moment of inertia for the rotor. Okay, so what is the equation? The equation that is going to follow will be similar to the spring mass system. So here this is, you have K, this is you have, and then how do you write? Mx double dot plus Kx equal to 0. This one, similar analysis you can do. You can apply the solid mechanics. You give a twist by theta, you know, so then if you twist like this, there will be a rotational spring which will be applying in the opposite direction, and if the K is the rotational spring constant, so what you get? You get K times theta, which will be the opposite torque which is produced when you rotate it by theta. So you get K theta, opposite, so it's minus, and that is equal to J times theta double dot. So this is the, what is this one? This is angular I times alpha basically, right? So this is the torque, this angular acceleration. So this is angular acceleration. Okay, so what you get? Equation is J theta double dot plus K theta equal to 0. So you get the same equation as this one, or simply you get theta dot equal to K over J theta equal to 0. So this is the equation which will be here. Now you have to find out what is K. So J is given for the rotor, but what is K? So in order to find out for the shaft, how do you find out K? So K will be, what I mean to say is, if you apply a torque T, for example, so how much theta you can change, right? So this is analogous to, as we have done earlier. So in case you have forgotten the formula, you can actually remember the simple formula for the axial bar. If it has E and A, E being the Young's modulus, E the area of the bar. So the stiffness for this one was K equal to EA over L. So, or simply, their K is nothing but P over, so displacement is delta. So if you apply a P here, so del P over delta equals EA over L, right? Or you have delta equal to PL over EA. So this is for the unidirectional stretch for a bar. Both systems are same, but instead of P you have to T, for delta you have theta, and so on. So if you K, in this case BK will be, instead of E you have G here, right? So G comes into picture in case of torsion. So all solid mechanics things you have to remember. So G and A, instead of A you have IP, this one, so GIP. So K is equal to EA over L. So instead of E you have G, instead of A you have IP, and L also L here. So L is from here to total length of the shaft in this case. Yeah. So you have K equal to like this. Hence, what you get is omega n. You can actually find out from here what is omega n in that case. So omega n equal to root big K over J in this case, and big K is G IP over JL. So this is what omega n you get in case of a rotor which connected to a shaft. The one end is fixed, the rotor you give a small twist, let it oscillate, then in that case the natural frequency in terms of radian per second, you get this expression. Yeah? And so on. So you can apply in many other systems as well. So remember, although we have a spring and mass like this one, but this also implies this system as well, and many other systems. So if you understand this one as simple as just a spring and mass, you can also understand the other system as well. So this is just you can also think this as representation rather than actual spring and mass only. Okay. So now you should also know that there is not only one way of deriving these equations. So if you see the history of mechanics, there has been different kind of philosophies. One of them, what we have done here is Newton's law of motion we have employed. However, energy methods also we can apply actually. Yeah. So simple example. For example, if for a spring mass system, if you want to find out apply the energy method, how will we apply? So you give one disturbance and this starts oscillating, then we will say that the potential energy, the potential energy, the summation of potential energy. So potential energy plus kinetic energy equal to a constant. So that's what we will apply. Okay. So in this case, what is the potential energy? Potential energy is in terms of, we can write in terms of a spring basically. So how much, so potential energy is given by half kx squared, so that you know, right? So if this is x equal to 0 position, so if this is up here, for example, potential energy is more stored in the spring. If it is here, again it is more. So kx squared is the potential energy. Kinetic energy will be half mv squared. So this is m, and x dot square is equal to a constant. Let's call this a naught is the constant, equal to a constant. So this is energy, and that we want to make it constant. That means if we take a derivative of this with respect to time, then it should be 0. So take a derivative. Take a derivative. Derivative of the above with respect to time. Okay, and then what do we get? We get half k, and then you have this times 2x dot, okay, then plus half m, and then you have 2x dot and then x double dot equal to dA naught over dt is equal to 0, because A naught is a constant. And now we can see half, we have half here, so multiplied by 2, so all they cancel out. Okay, so here we have x dot here, x dot here, so we get rid of this. Yeah, so we have k here, x here, so we write kx. Okay, and then here m x double dot, so plus m x double dot here equal to 0. So what you see is we get the same equation that you get by the Newtonian method, right? So from the energy method only we are getting the same equation. So remember that there is not only one way of actually deriving this equation, and especially for dynamics, for theory of vibration, there are different ways. In fact, energy methods in some cases are easier to actually get equations, governing equations. Yeah, although this is covered in the advanced dynamics classes or the advanced theory of vibration. So here we will not be using energy methods in your class, so we will be whatever we do, we will be using mostly the Newtonian method only. Okay, also remember that when we are drawing a spring like this and mass like this one, this is also representation of a continuous system into a lumped system like this one. Okay, this is convenient actually. In real life, you know that even the spring, as I said earlier, we are assuming it to be a massless, but it's possible that it's not massless, and then if you want to derive, you can actually derive it. So let us say there is only a spring only, a heavy spring, right? They say a spring like something like this one, and there is no mass, there is no external mass, but it may have some mass. Yeah? Total mass, say total spring mass equal to m in this case, right? Or make it capital M just to distinguish from here, so we call it like this one. Okay, now if length is L, let us say L like this, and now we are giving a small disturbance in this case, then what happens? Can we represent this as a spring mass system like this one? Yeah, so K, here also we have the K, that's the same K, but only thing is here is the mass is distributed. This is a continuous, so the mass is everywhere. It's not just like lumped at the end. If that is the case, then we know that if we are if this point, if you is at, let's say, last point, let us say, if this has moved by x, and then you will know that all these will also move. Okay, so let's say from here to here, this is the y system, so meaning that this is y equal to 0 and this is y equal to L here, right? So this is y equal to top, this is y equal to 0, here is y equal to 0, here equal to y equal to L. So x as a function of y, we will give it as x multiplied by y only, right? So if y equal to 0, we have x, so yeah, that's fine. So x at y, so if y equal to 0, we have here we have displacement will be 0, but here when we have when y equal to L, we have to write like this, x times y over L, yes. Then when y equal to L, we have, let's call this is x naught. It's a confusion. Okay, now x naught is the displacement at this end, x naught. So if x represents the displacement deflection along the length, so x as a function of y will be given by x naught y over L, where x naught is the deflection at the end of the spring, so that when y equal to L, you have x naught, right? So at y equal to L, you have x naught, and at y equal to 0, you have x naught times 0 over L, which equal to 0. So this is a linearly like this one. Okay. Now, what we want to find out, the lumped mass, what is the equivalent lumped mass for this one? And for that, we have to write the kinetic energy we have to find. Okay? So equivalent kinetic energy. The kinetic energy, let's say T equal to half M effective times x, whichever point we are going to say. So let's say this is a point A and point B we are saying. So we are interested in point B. So x half M square. So what it is saying is find out the velocity at the point where you want to find out the effective mass. Let's say we want to find out at point B, so xb dot square multiply by this one. This is the kinetic energy. If we know the kinetic energy T, if we equate like this one, so we can find out M effective. M effective will be equal to 2T over x dot B square. This is the M effective is nothing but the M, this M, the equivalent, the lumped mass. So for this one, we want to find out. So how will we find out? So how will we find out? We want to find out what is the T as a function of y. Okay. So total mass is M. So let's take one slice. So this continuous system. So let's take one. This is a spring, right? So we are taking dy here. Total mass in this case will be dm will be equal to total mass m over L divided by dy. This is the total mass. Okay, so will be half dm times x dot square. So what we get here is x dot. If the velocity x dot, if x dot is there, so velocity here also will be linearly varying. So it will be highest here and then linearly varying between this and this. Okay, so similarly we can say that x dot y will also linearly vary. So x dot y over L like this. So half m and v square. So v will be x dot square. Okay, so this will be dt. So dt change in the dt is the basically the kinetic energy for that element, the small portion that we are interested in right now. So dt half dm, and dm is nothing but m over L dy, and x dot y is nothing but x0 naught y over L, and this is a square. Yeah, so we get dt equal to half, and then we get m, then x dot square, and then L cube here. So half m x dot naught square over L cube, and then we have y square and dy like this. Yeah. Okay. So total T will be T equal to, we have to integrate from 0 to L, and then we have half m x dot square plus L cube, then y square dy, and will be equal to, so we have half m x naught dot square L cube, and then you have y3 over 3 integrated from L over 0, right? So what we get is half m, and then this one we have x dot naught square L cube, and here also we get L cube over 3. So L cube cancels out, and what we get is half m over 3 and x dot naught square. Okay, now compare with this one. What it says? It says if you want to find out the m effective, we get 2 times what the T is divided by this one. So m effective we can find out here. So let's do it here only. So m effective, basically m effective for this system, for the spring, will be equal to, let's see here, so equal to 2 times T is half m over 3 x dot square divided by x dot b square, and at b we have x dot naught. So x dot naught square. What do you get? So this and this will cancel out, 2 to cancel out, so what you get? M over 3. So what it tells you that M effective for this one is M effective for this case will be equal to M over 3. So basically this, which has a continuous mass or distributed mass over the whole spring, can represent it as this system where a spring you can represent it as now massless, but M is equal to M over 3. Okay, so both are equivalent. Here there is no external mass, but there is a distributed mass for the spring. Total mass is M. This you can assume this to be equal to a massless spring of the same stiffness, but there is a mass attached to it whose mass is equal to mass of the spring divided by 3. So this and this become equivalent. So what you see here is a distributed or system is actually is being represented by a lumped system. Yeah. So making this makes it convenient. Yeah. So my point is if you look at the spring mass system, this represents many things. It may represent a continuous or distributed system like this one, or it can also represent the example I showed, a shaft which is fixed and at the other end there is a rotor, or it may also represent a cantilever beam at the end of which there is a mass put there. So just a spring and mass is very powerful tool basically, and hence we will focus on this only. We will not focus. There may be some examples we will be solving like this one, but if we solve, we understand this one, we understand this as well. Okay, so hence we will be focusing more on this. Okay.